Alright, so this is LeetCode 338, counting bits. So it says given an integer n, return the array, return an array answer of length n plus 1 such that for each I is going to be greater than or equal to 0. And it's also going to be less than or equal to n. In that instance, basically every value is the number of ones in its binary representation of I. So what does that actually mean? Let's look at this example. Let me make this black. So we look at example 1. So our input is 2, right? And our n is 2. What they want us to do is basically return an array of n plus 1, where basically we're going to count up to 2, starting from 0, so 0, 1, 2. So this is in base 10 or non-binary. This is kind of like, numbers like that you would learn in math, like one counting by 1, 2, 3, 4. And then what they want us to do is return an array where each value is converted to binary. So what's 0 converted to binary? Let's go ahead and write our bases of 2 so that it can make be a little easier. So bases of 2. So to convert to binary, we're going to start with base 2 to the power of 0, 2 to the power of 1, 2 to the power of 3. And I think for this instance, we only need these bits. Basically, we're going to look here. So 2 to the power of 0, or 2 to the power of 0 is equal to 1, right? So we want to see in these positions, if it's a 1, then it means that that bit is on, or represented by this base of power of 2. So in this instance, 0 in binary would just be 0. However, for 1, we would use this bit here. We would use, use my mouse so you can actually see. We would use this bit here to represent 1 in binary, because 2 to the power of 0 is 1. You can watch a video on converting from base 10 to binary, but yeah. And then to represent 2 in binary, we're going to use this bit here. So it's going to be 0, 1. Actually, not 0, 1. It's going to be, I believe, 1, 0. Right? Because we're going to use this bit here, because 2 to the 1 is 2. And then we're going to have a trailing 0, because this bit's going to be off. Okay. So now that we've converted it in binary, our values to binary, right? Here are our values. What they want us to do is return an array where we count the number of ones in each of these base 10 values in binary, like the number of ones in their binary representation. So in this position 0, there's 0, 1, so that's why we would have a 0 there. And then here we have 1, 1, right? So that's why we'd have a 1 here. And then here we would have 1, 1 also. So that's why we have a 1 here. Let's say that this was 1, 0, 1, then we would have 2 in this position, because there would be 2 ones. But for this instance, it's not that. But I'm just trying to showcase what we're actually returning. So we're just returning the number of ones in the binary representation. Okay, so yeah, so how would we actually do this? So you could do this multiple ways. You could do this like the kind of naive solution would be to get every value, convert it to binary, and then count the number of ones. So let's say that we had 1, 0, 1 in binary, right? And we wanted to count the number of ones, well, we could have like a count variable, and then we could modulo this by 2 and do some math to see if this is 1 or not, and then we can just truncate it by using integer division. That's the naive solution. That solution would come out to being O of n log n, because you're constantly dividing our number by 2, which is a logarithmic time complexity, and then we're doing it for up to n numbers, so it'd be n log n. So that would be the time complexity. If we scroll down, that's for the naive solution. So they said that it's very easy to come up with that solution, and then they want to see if we can come up with a solution that uses linear time and possibly a single pass. So it might not be as intuitive as it seems, but we're actually going to use something called dynamic programming. So we're gonna start with subproblems, and we're gonna use those subproblems to build up our solutions to getting the actual output. So, and that's gonna give us a faster runtime. So instead of n log n, we're gonna have O of n, which is much faster. This is much faster than this. Okay, we might sacrifice on some space, so our space complexity might go up, but we're gonna still be faster in the time. Okay. To visualize this, I made this little chart, this little table, I guess. Okay, so you can see I labeled the columns. So on the top left, there's the input in base 10, and then in the middle is the input in binary. So these numbers, I'm going to use my mouse so you can see. These numbers here are the input, is basically this value converted to binary. And then just for help, I added the bases of 2 and then what their value comes out to. So 2 to the power of 0 is 1, to the power of 1 is 2, to the power of 2 is 4, and so on, to the power of 3 is 8. And then the output for our function is going to be here. Okay, so let's walk through. So here, right, like we did in our first example, 0 in base 10 is this in binary, and there's 0 ones here, so that's what our output would be. 1, we would have 1, 1, 2. In binary, we would have 1, 1, because we're utilizing this bit right here. We're turning this bit on and nothing else, because that represents 2 in base 2, right? So we'd have a 1 here. 3, we would utilize this bit here, and this bit, we would have them both turned on, so that's why it's 1, 1 here. Let me use this color. That's why it's 1, 1 here, because we're representing 3, so we'd have 2. Okay. And then 4, 4 has 1 bit, 1, 1 actually on, so we would output 1, right? And then 5 has 2, 6 has 2, 3 has 3, and so on, right? So what I'm trying to get at here is that we're doing some repeated work that we could optimize our solution to basically to gain that O of n time complexity. So as you can see, it might not be as apparent, but realistically, I'm going to box it in yellow. This is pretty much the same as this, right? These two sections are identical, right? It starts with, let me use my mouse again, it starts with 0, 0, 0, 1, which is the same here, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. So they're identical, right? The only difference between these values is that there's a 1 in this place, in the 2 to the power of 2 place, right? So what we could do is basically, what we could do is store the, we could store the output of these previous values, and what we can do is just basically do 1 plus we look back at whatever this output was, right? Because this is, these 0, 0s match with this 0, 0, so there's a difference. The positioning would be difference of 4, right? So we're looking back at 0, the 0 input. So we're going to say 1 plus however many ones 0 had, right? However many ones 0 had. And what about for 5? We're going to do 1, because this new bit here, this 2 to the power of 2, is 1, plus however many ones 1 had, this 1 here. So you could see, let me do this here, you can see that again, there's an offset of 4, right? We're looking back 4 positions here to look at 1, okay? So what we're gonna do is we're gonna, as I said earlier, we're gonna sacrifice on our space to make the time complexity faster. So we're gonna create an array, and let's just call it DP array, right? And then this DP array is gonna store the outputs of our previous values. So this 0 is gonna go here. My pen's kind of bugging out. This 0 is gonna go here, right? And then this 1 is gonna go here, and so on. We're just gonna tack on these values. We'll just tack on the first 4. Okay. And then let's try to, instead of having this in words, let's actually write out what it would be like in an equation. So what this would come out to be would be, basically we're doing this 1, we're counting this greatest power of 2. Currently our greatest power of 2 is this position, right? The third position, the 2 to the power of 2. So we're doing 1 plus whatever we had at 4 positions beforehand. So we're going to do, the equation is going to be 1 plus, we're going to look at our DP array, right? We're going to look at our DP array, because this is what's going to have our values, our previous outputted values. We're going to look at our DP array, and we're going to say we want to look at the 0th value, right? We want to look at this 0 value. So how can we do that? Well, we can do the current n that we're at, which is 4, minus 4, basically, right? So we get at 0. So we do 4 minus 4, right? So that would give us, this would come out to being 1 plus, what is DP array of 4 minus 4 goes out to being 0, right? So this is the 0th position, so there would be 1 plus 0, which comes out to being 1, right? So that gives us, that checks out with this output here, right? Okay. Because because we're not going to have these strict values here, we're going to have to use some variables. Let's try to deduce what these variables actually are. So this value here that my mouse is going over right here, this is going to be our current n value. So let me do it in yellow. This is going to be n, right? And then this is going to be, what is it going to be? Right now we don't really know, actually. It seems like it could just be whatever maybe it's the same value, maybe it's n2. But let's go a little further and let's see if we could figure out what that's going to be. So let's say let me scroll down slightly. So what if we're gonna try to let's try to see what 8 is gonna be. Let's try to like basically do exactly what we're doing here with the equation for 8, right? So let's bring this down here. Okay, so 8 is gonna be 1, counting this 1 here, right? Plus, is it gonna be an offset of 4? Let's see. What would be if we look back 4 positions at 4? That would be that would give us another 1, 0, 0. But as you can see, 8 in binary does not have 2 1s in it. It only has 1 1. So realistically, what does the remaining zeros, what do these zeros represent? What is this in binary? Or in base 0 or in binary? This is 0, right? So realistically, this, let me do it in it's orange. Realistically, we want to do 1 plus looking back all the way back to the starting 0, right? So we're going to do 1 plus dp array of n minus what would it be? Minus let's just actually fill them in with numbers first. It would be 8 minus 8, right? Because in this previous example, we said that this first value is going to be n, which is this is n, right? This column is n. So all these values are n. So 8, this is our n. And then because we want to basically, this is kind of hard to explain, so sorry if I'm stirring it a lot, but instead of looking at this here, those 3 zeros and trying to count however many ones there are, basically what we can do is just look back at one of the previous solutions, which is all the way back at our first solution, which is of input 0, right? So it's 8 minus 8. Okay. So off of this, let's see if we can actually deduce what this second value is going to be. With this, is this 4 always going to be the matching number here? It's not always going to be the case, I don't believe. I think let's test it out with 5. Let's test it out with this test case of actually just to do with 6. So let's put this all the way over here. So what's this going to be? It's going to be 1 plus dp array of, hopefully you guys are getting the pattern already, but so what does we're using this 1, right? Plus, so what does this 1 0 look like? It looks like this 2, right? So we're looking 6 going back to 2, that's 4 positions, so it's 6 minus 4 in our DP array. So this is basically the index that we're going to look at, right? And we can write out the indexes here if it helps out. So 0, 1, 2, 3. So we would look back at the, what is it going to be, the second index. So we're going to look at this index here, and we're going to do 1 plus 1, which gives us our 2. So back to deducing what these values actually are. This is n, right? The left value is n in our brackets, but what's the right value? So we know that it's, off of this example, we know that it's not going to just be 6. It's not going to be whatever n is as well. It looks like it's whatever is the greatest power of 2, right? In this example, the right value here where my mouse is going over, this 4 is the current greatest power of 2 that we have on, right? That is set to 1. Here is the current greatest power of 2, which is why we do subtract by 4. And then at 8, this example down here, if you can see my mouse circling it, this example, we're doing 8, which is the n value, which is this value here, minus an offset, which is basically the offset is the current greatest value of 2, which is 8 here. So the whole formula is going to be 1 plus dp array of n, so the current value that we're trying to calculate, minus greatest power of 2, right? Okay, and then that's in the bracket because this is going to come out to be an index, right? I'm just gonna get rid of that. It's horrible. So okay, so yeah, this is what we're gonna do. This is our equation for our DP solution, and let's try to deduce this time complexity. So right, so off the bat, we are going to have to calculate, we're always going to have to calculate n values, right? We're always going to have to calculate whatever the input is n. So like say that say the input was actually we might have to calculate n plus 1, but let's say that the input was 8, right? We're going to have to calculate 0 through 8, so that's actually 9 values. And then we're going to have to say that input was 9, we're going to do 0 through 9, which is actually 10 values, because we include 0, right? So our time complexity, yeah, so as I was saying, the time, I don't know why my pen's not working. Time, my pen or my laptop is lagging. The time, I think it's because I was so zoomed out. The time is going to be O of n, and then the space. So automatically, this is way better than the O of n log n. This is significantly better. And then, if you don't believe me, you could look up at the Big O cheat sheet and see the different performances of these time complexities. So for space, this one we're sacrificing on space. We're using a little bit more space to get our time down, right? So this space we're going to use, we have to store a DP array, an array of our previous values, so that we could use those values to calculate our new ones in a fast way, right? And then what's this DP array going to get up to the size of? Well, it's going to get up to the size of, it's going to get up to the size of n plus 1, I believe, right? And then technically this is really O of n plus 1, but I think in big O notation you just drop this +1, I believe. You might not. I'm not too familiar with that. I kind of forgot that concept, but it's either big O of n or big O of n plus 1, but realistically I think this +1 is negligible. So because that, I'm just going to call the space O of n. It also might be O of n plus 1, but I think that +1 is negligible. We're here on LeetCode, and I kept the whiteboard over on the left so it's easier to just kind of reference our algorithm. So as I said, we're going to utilize a DP array, right? Or it's just an array, right? But it's just a normal array, but the values in it are using the principles of dynamic programming. So basically, we're starting with smaller problems, and we're using those small problems, the solutions to the small problems, to build up our solutions to the other problems, so that we don't have to recalculate previous solutions, if that makes sense. Basically, we're optimizing it by not here. If you can see here, what I have boxed in yellow, we're not recalculating this because we're utilizing our DP array, but we're sacrificing by using some space. Okay, so we're gonna start our DP array, and it's gonna just be it's just gonna have one value in it. It's just gonna start with 0. I chose 0 because in our constraints, the lowest n can be is 0, right? And we know that 0 in base, or 0 in binary, is just has 0 1s, right? The output is going to be 0. So we know that this starting value can just be 0. It's just like our base case, if that makes sense. Hopefully the explanation made some sense. So we're going to start off with 0 to start off our dynamic programming solution, and then we're going to have a value that's called greatest power of 2, and that's just going to start at, what is it going to start at? Well, if we zoom in back in our, oops, it's going way too much. Let me use my mouse, I think it's a lot easier. Oops. If we look back up here, what's the first greatest power of 2? It's 1, right? Because 1 is a power of 2. It's 2 to the power of 0. So we're going to start this at 1, right? Greatest power of 2 is going to start at 1. Okay, and then we're going to do our for loop because we have to calculate n plus 1 values, right? So we're going to do for I in range. Well, what's as you know, range can take, you could give it different types of parameters. So we're going to give it a starting value and an ending value, right? So this is just a comment. The starting value is going to be, what are we going to start at? Since we've already initialized our DP array with 0, meaning we've already calculated this first value, we can just start our I at 1. And then what do we want to go to? As I said, we want to calculate n plus 1 values, because in this case, in this situation, n was what? It was 8, I believe. Yeah, it was 8. So we calculated 9 values because it's 0 through 8, including 0. So that's 9 values. So we would do 1, and then the ending value is going to be n plus 1. Okay. And then what we're going to do is here we need to decide when we're going to change our greatest power of 2 variable. Basically, what we're going to do is at each value, right? So right now, greatest power of 2 is 1, right? And then what we're going to say is n is, in this situation where our mouse is at, n is 0, right? So 1 times 2 does not equal 0, so that's not a greatest power of 2. 2 times 1 does not equal 1. 2 times 1 does equal 2. So that means that we've found a new greatest power of 2, meaning that there's a new most biggest power of 2 right here, this value here. So the condition is going to be if greatest power of 2 times 2 is equal to we're using n, so I'm going to change this value. I'm going to change it from I to n. So if it's equal to n, then that means that we found a new greatest power of 2. So we can just reset greatest power of 2 to be n. Okay, so that's how we're going to reset our greatest power of 2. And then now we're just going to now realistically we just have one more kind of line of code to write, and that's basically what we've deduced to be our dynamic programming kind of equation we're going to do. Before we get ahead of ourselves, what are we actually returning? We're returning an array, right? So we're going to return this DP array, right? We're going to return, after we've populated all the values, we're going to return DP array, right? So what we need to do is we need to append to the DP array after we've, calculated our values using this formula. So we're going to say DP array dot append, which is basically append to the end of the array right here. DP dot append 1 plus, and I'm just copying what we have here on the left, 1 plus DP array of n minus greatest power of 2. And I just spelled out 2 instead of using the actual 2 value, but that's just what I have for the variable. Yeah, and then we just return the DP array. So that should come out to be the solution, unless I made a mistake. Let's see. I made a syntax error. I didn't add the colon. So, I actually made an error words. So, okay, so I made another dumb error. It's basically this. It's Python's indenting that basically this appending operation was in the if statement. We want it to be untabbed, so it's underneath the if statement right here. So it's not inside of the if statement, but it's outside of it. So we want this to happen on each iteration of the loop. Okay, so now let's run it. Yeah, so that works. Okay, so here's the big O cheat sheet. So as you can see, these time complexities, or these big O values down here are the fastest. So O of log n and O of 1 are the fastest, and then O of n, and then O of n log n. So we sacrificed on space, but we got our time complexity to be faster than what our brute force or our naive solution was in the beginning, which was O of n log n. Yeah, so thank you for watching.